Hello guys, welcome back to Maths from My Desk. In this video, I'll be deriving what I think and what many other people think is the most beautiful equation in mathematics, and that is Euler's identity. We have e to the I pi plus 1 is equal to 0. The reason why so many people think it's a nice equation is because of how elegant it is. We have e, a very nice irrational number, I, the imaginary number, the square root of -1, and pi, also an irrational number, put in a very elegant equation where you add 1 and you add 1 to e to the I pi and you simply get 0. So in this video, I'll be deriving Euler's identity using the Maclaurin series expansions for e to the x, cosine of x, and sine of x. So let's go ahead and start the derivation. So first, I'm going to write out the Maclaurin series expansion of e to the x. So we have e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5th over 5 factorial. And this would keep going on. So we have a general term for e to the x as x to the n over n factorial. So we can describe e to the x as the summation from n equals 0 to infinity of x to the n over n factorial. So now, in order to actually derive Euler's identity, what I'm going to do is I'm going to set x equal to I, the imaginary number, the square root of -1, times some arbitrary variable that I can pick here, let's say theta. So now I'm going to rewrite the Maclaurin series expansion, but with I theta instead of just x. So let's do that. So I have e to the I theta is equal to 1 plus I theta plus here we have I theta squared over 2 factorial. So wherever I see x, I just replace that with I theta plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial. And we get a general term of I theta to the nth power over n factorial. So now I can go ahead and simplify this since I can figure out values. For I. So I know that I is just equal to I, obviously. So this is I to the first power. I squared, this is the square of the square root of -1, so we get -1. I cubed, this is -1 times I, which is -I. I to the 4th, this is equal to -I times I, which is, that should be 1. Then we have I to the 5th, which is 1 times I, which is just I. So now whenever I see I, I'm going to go ahead and replace, I'm just going to go ahead and plug in these here. So I can write I theta is equal to 1 plus I theta, because I is equal to I, obviously. Then, I squared is -1, so I can write this as minus theta squared over 2 factorial. So let's just pretend there's a 1 here, because -1. And we have theta squared, obviously, plus I cubed is -I, so we have -I times theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial. So, and this is going to go on, obviously. So all I did is I plugged in these values for I wherever I had to fit them in. For example, I cubed, I plugged in -I. So now what I'm going to do in order to be able to derive Euler's identity is I'm going to set all the terms, I'm going to separate all the terms with I from the terms with theta only. So let's go ahead and do that. So e to the I theta is equal to, so first let's put the terms with theta only, or anything that doesn't have I. So we have 1 first, then we have minus theta squared over 2 factorial, then we have plus theta to the 4th over 4 factorial, and that's all I have here. And then now I'm gonna have all the terms with I. So I can factor I out, and I have I theta. Oh, sorry, I just factored I out, so theta is out. I is out. So we have theta minus, minus, because here there's a negative, and I'm gonna keep that here, minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial. And you might recognize that this is just the Maclaurin series for sine of x and for cosine of x. So over here we have the Maclaurin series for cosine of theta, my bad. And here we have the Maclaurin series for sine of theta. We can define sine of theta and cosine of theta using Taylor series as, well, we have sine theta is equal to the summation from n equals 0 to infinity of, we're going to have negative 1 to the n times, we have, I believe, x to the 2n plus 1 divided by 2n plus 1 factorial. And cosine theta is just this, but whenever you see here plus 1, you remove that. So cosine theta is the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. And so this, if you plug in your values for theta, you're going to find that these are the Taylor series expansion. So we can rewrite e to the I theta equals cosine theta plus I times sine theta. So this is the general form we get for Euler's identity. And where do you get pi? Well, let's just say that theta equals pi. So let's go ahead and plug in pi to this equation here. And we're going to get e to the I pi is equal to, well, what's cosine of pi? Cosine of pi is negative 1. So we have negative 1 plus I times sine of pi is just 0 times 0. And we therefore obtain, let me do that in a new paper. We therefore obtain that e to the I pi, let me make it clear here, e to the I pi is equal to negative 1 plus 0. And if I go ahead and add 1 to both sides, I get the beautiful equation e to the I pi plus 1 is equal to 0. And we have therefore derived Euler's identity using, as you can see here, a bunch of Maclaurin series expansions. So we used e to the x, cosine of x, theta in this case, and sine of theta. So this is how you derive this very elegant identity. I hope you guys enjoyed this video, and I'll see you soon.